Post hocs, basically, and there are exceptions, compare each level to every other level. We use these when A, we have no idea what the pattern of differences will be, or B, we're interested in more than k minus 1 specific group comparisons, or C, we're lazy. All of these are perfectly valid reasons to do post hocs, but they come with a price. You know generally that we will expect to do alpha correction, which is reduce the p-value that it takes to call something significant. This means you have less statistical power, and you're less likely to find significance. Now, if we have alpha corrected post hocs, if we have to do that, don't we also have to worry about alpha corrections in planned contrasts? Maybe we do. There is some discussion of the fact that even here we might need to do some alpha protection. We'll return to this later. Now, the underlying concept we need to understand before we consider post hocs is family-wise, or sometimes it's called experiment-wise, error. Each comparison we make, say group 1 versus group 2, has a comparison-wise error rate. That's the alpha for each comparison. The family-wise error is the probability of making a type 1 error for the set of all possible comparisons. At the bottom of this slide, you see the formula for experiment-wise error, where C is the number of comparisons you're making. This is the official most correct formula for family-wise error. To illustrate this, if you're comparing 3 groups, A, B, and C, you can do 3 total comparisons, AB, AC, and BC. Plugging in those 3 comparisons into the formula at the bottom of the slide, the family-wise error is 0.14. A slightly less accurate formula, but a simpler one to calculate on the fly, is to multiply the comparison-wise error by the number of comparisons being made. Let's look at that on the next slide. The approximation of the experiment-wise error rate without any adjustments would be comparison-wise alpha times C, where C is the number of tests. That comes out, as you see at the bottom of this slide, to 0.15. 2 of the more popular post hoc approaches with alpha correction use these 2 correction formulas in reverse. Bonferroni uses this simplified formula. Dunn-Sidak uses the correct formula for family-wise alpha from the preceding slide, but we're getting ahead of ourselves. So what I wanted to do is talk us through a couple of the major contrasts. More or less, I've tried to highlight the more important ones, and the less important ones will be mentioned, but I don't expect that we'll do these together. We will very briefly discuss what these different options mean, but don't worry about memorizing them, as we'll use at most a few of them, 2 or 3. The first one is Bonferroni. The reason I put that one first is because it's the one that we've already talked about the most, and it's widely used, so let's just formalize it a little bit. Bonferroni simply calculates a new pairwise alpha to keep the family-wise alpha value at 0.05. It turns out that as you saw, a rough, not perfectly accurate way of estimating family-wise alpha is the alpha of each comparison times the number of comparisons. So if you have 5 comparisons, each at alpha equals 0.05, then your family-wise alpha is going to be 0.05 times 5, or 0.25. That's way too high. Bonferroni compensates for this by dividing your desired alpha by the number of tests. So if you desire 5 tests and you want your family-wise alpha to be 0.05, then you're going to divide that 0.05 by 5, making each unique comparison have a comparison-wise alpha of 0.01. So you test each post hoc at alpha equals 0.01, and this maintains a family-wise alpha of 0.05. It's very straightforward. Dunn-Sidak is basically the same as Bonferroni. Instead of dividing alpha by the number of tests, it reverse engineers the more correct formula for family-wise alpha, as shown on the next slide. The only difference from Bonferroni is that this test uses the correct formula for adjusting the family-wise alpha and doesn't just divide the family-wise alpha by the number of tests. It will typically produce almost the identical result, as you can see. It's just a little bit more precise in correcting the alpha. You will notice that you almost never see this correction in the literature because it's a step up in complexity without any real benefit over the Bonferroni. Next, we have Hochberg's G2. You're not really going to use that, so very briefly. I put extra background information here, but in a nutshell, what happens is this. First, you run the unadjusted post hocs. Second, you order them from smallest p-value to highest p-value. So let's say we have 3 groups, so that produces 3 contrasts. The first contrast with the smallest p-value, you test unadjusted. The second contrast with the next largest p-value, you test with an adjustment of alpha divided by 2, correcting now for 2 tests. The third contrast with the largest p-value, you test with an adjustment of alpha over 3, now correcting for 3 tests. Obviously, this makes it more likely that your significant results will stay significant. The problem with this approach is that it's pretty opportunistic. That is, it doesn't order the contrasts a priori based on theoretical importance. It orders them post hoc based on p-values. I've never personally seen this published in a psychological study. Now we have Chaffee. In graduate school, I was taught that Chaffee was the most conservative of all. So what does Chaffee do? Chaffee is conservative because it not only corrects for all pairwise or simple comparisons of means, but also for all complex comparisons of means. You see this at the bottom of a slide, comparisons involving 2 or more means at a time. Thus, it is the least powerful and should only be used when you have such complex comparisons. Then there is LSD. LSD is kind of a basic one because it is no correction at all. The Fisher LSD test, or least significant difference test, draws on the rationale that if an omnibus test is conducted and is significant, the null hypothesis is incorrect. If the omnibus test is non-significant, no post hocs are conducted. Since type 1 errors are conditional on the null hypothesis being true, this test takes the position that there is no type 1 error because the omnibus test proved, in quotes, that the null hypothesis is false. So, by conducting an omnibus test first, one is screening out group differences that exist to sampling error, and thus reducing the likelihood that a type 1 error is present among the means. This is the most liberal post hoc of all. One instructor, Andy Karpinski at Temple, goes so far as to say that it is too liberal and not valid, and we should be suspicious of anyone who uses it. Now, there's Tukey. Tukey comes highly recommended by a number of authors, including Andy Field and the guy I just mentioned, Andy Karpinski. So let's have more of a look at that. Tukey basically works like the LSD test. It is less liberal, however, because instead of using the T distribution, sometimes called the student's T distribution, it uses a more conservative student's Q distribution of sampling error. That helps guard against type 1 error. So what about this Dunnett? The Dunnett test is similar to the Tukey test, but is used only if a set of comparisons are being made to one particular reference group. So for instance, if we have several treatment groups that are compared to one control group, the reference group, then we might use Dunnett. Since this is rarely the comparison of interest if we're not doing contrast but we're doing post hoc, the Tukey serves a much more general purpose, and I recommend the Tukey test. Now we have the student Newman-Kules, SNK for short. This text comes from Andy Karpinski at Temple University. He says student Newman-Kules is somewhat popular, but is problematic because it is too opportunistic. It uses a Tukey approach, but adjusts the p-values much like Hochberg. It uses a similar graded significance thing that we talked about for Hochberg. So what SNK does is it develops a correction that is sensitive to different levels of comparison. It literally changes the critical value based on how close or how far the means are. It's all done post hoc. It ranks the means from far, so these are going to be the most significantly different, to close. These are going to be the least significantly different. For the means that are far apart, it uses a larger critical value. In other words, little or no adjustment at all. For the means that are close together, it uses a smaller critical value. It's entirely data-driven and opportunistic. And it basically says that the bigger the mean difference, the less I'm going to adjust it, the more likely it's going to be significant. Now we have a few more of these multi-authored post hoc tests. You'll notice there are two that are very similar. They start with REG. These stand for Ryan, Einert, Gabriel, Welsh. As you can see by date, Ryan wrote it first, modified by Einert, Gabriel, and Welsh, so they decided to give credit to everyone. It becomes the REGW. Those are the first four letters. So then we have two. We have a Q and an F. The Q one is based on studentized range, the same thing that Tukey and Dunnett are based on. The studentized range sometimes is called the Q distribution. Like some of the other indices, it adjusts the critical value based on how far apart the means are. Then if there's Tukey, what's Tukey's B? Tukey's B is, according to Karpinski, the definition of an out-of-control post hoc. What will happen is that you'll have Tukey, which people like, with an omnibus significant difference. Then you'll have student Newman-Kuhl's, which is extremely liberal. To resolve the debate, should I use Tukey or student Newman-Kuhl's, both of which are based on the Q distribution, Tukey's B says, let's not let there be a debate. Let's compute the post hoc under both tests and take the middle. So this slide comes from Karpinski, who says you should never use it, and I concur. As you can see, there are a couple of tests available when equal variance is not assumed. So if Levene's is significant, come down here. Why? The short answer is that planned contrasts make an assumption of homogeneity of variance. Just like you really should not use the F statistic if you do not meet homogeneity of variance, you shouldn't really do planned contrast if you do not meet homogeneity of variance. Games-Howell is a response to non-homogeneity, and we'll go over how that works next. I should add that Paul Games was my ANOVA teacher at Penn State, so it's always cool to me to see his test in SPSS. But think about how we deal with that. For the F test in a one-way ANOVA, and only in a one-way ANOVA, we have possible corrections like Brown, Forsyth, or Welsh. Even though SPSS does not provide a correction to the F test in multi-way designs, it will still offer the Games-Howell correction for the post hocs. So that's kind of useful. To make the long story short on this slide, when we have homogeneity of variance, you will notice we use the same standard error of a difference as a denominator in all our post hocs. That makes sense, and it's powerful. The standard error is based on the total sample, and that'll be as small as possible. Games-Howell makes two major adjustments. First, instead of assuming homogeneity of variance, it recomputes the standard error for each paired comparison based on the variances of only the two groups being compared. Second, to deal with type 1 error inflation, it uses Welsh's correction, like we've seen a few times now, to the degrees of freedom. So what would you use? Pulling together recommendations from Karpinski, Andy Field, and Logic, here is the basic set of options, I think. If you have complex comparisons, like group 1 versus groups 2, 3, and 4 together, use Chaffee. If you're only doing pairwise contrasts, use Tukey or Bonferroni. Several authors prefer Tukey because it is less conservative, but what I like about Bonferroni is its simplicity. It's so easy to explain, alpha divided by the number of tests. And if you have unequal variances, use Games-Howell. Linking together contrasts and post hocs, this summarizes everything we've been saying these last 2 weeks. So, if your comparisons are planned, then if your questions are about linearity of the differences, you want to do orthogonal polynomials. If there are k minus 1 contrasts that can be represented orthogonally, like in the Viagra study, you want to use Helmert or difference. If you have k minus 1 planned contrasts that are not orthogonal, because you want to repeat a reference group or singled out group in more than one comparison, then use simple, repeated, or deviation contrast according to need. If you're doing post hocs, so you don't have planned comparisons, if you can justify no adjustment at all, use LSD. Normally, you'll want to do an adjustment where you then vary from relative liberalism with Tukey to simplicity but conservatism with Bonferroni. If you're comparing more than pairs of groups, you need Chaffee. And As we said, if you have unequal variances, use Game's howl.